Hello, we are Jun Park, Dong Han, and Yonghyun Jo. We are gonna talk about our work, a new metric for L infinity attack today. How robust is your model against perturbed input? In this image, with very small adversarial change, the model came to be foolish. Neural networks sometimes produce weird results, even with very small adversarial changes. This non-robust behavior of neural networks can be problematic when the models are used for decision-making in safety-critical systems such as autonomous driving and medical diagnostic systems. In order to determine whether the model is robust or not, we must define a metric to measure it. In past, adversarial accuracy was usually used to measure the model's robustness, but using one metric was not enough. So we are proposing a new metric that captures sparsity of a model against L infinity attack. We commonly evaluate robustness with adversarial accuracy, which tells you for which fraction of the data points there is no adversarial perturbation. Recently, there has been sparse adversarial attacks to modify the smallest amount of pixels in order to change the model's decision. In this case, we need a little different way to measure the sparsity of model. We used Cypher10 dataset to test the model. The Cypher10 dataset consists of 60,000 32 by 32 color images in 10 classes, 6,000 images per class. Images are divided into 50,000 training images and 10,000 test images. We simulated an attack scenario. Basically, we generate noise metrics based on the L infinity norm. The pixels of noise were randomly selected by using a uniform distribution according to the epsilon value for each RGB channel as shown in the formula on the left figure. And then, by combining original image with the noise, we generate a attacked image so as to feed it into a model. For example, in the noise image, you can see about 16 pixels were perturbed. And then we applied our L infinity sparsity algorithm to find the sparsity value k. This figure shows our pipeline to find the value k. As shown in the figure, after random sampling of multiple images per class, images come to be changed to the attacked images, and then we measured accuracy of the model to extract the sparsity k. Sparsity k. Here is the pseudocode and visualization of our algorithm. First, a test set is created by collecting a certain number of images from each class. Second, L infinity attack is performed using the specified epsilon value and the current k value for all images. Third, if the model correctly classified more than half of the images, it will increase the number k. In the opposite case, it decreases k, and then it repeats the sparsity check until k converges. The following is the part about the CAM sparsity metric that is currently being added. We discovered the following problems. It was difficult to obtain the minimum number of pixels required for modal disturbance. In order to measure sparsity more effectively, it is necessary to limit the area of the noise. It is more accurate to measure the sparsity of the image, specifically for the part which dominantly affects the output of the model. In this context, CAM sparsity limits the area of L infinity attack by using activation map. The pictures is the result of the L infinity attack process when CAM sparsity is applied. Let's discuss our experiment. We measured the adversarial accuracy and our metric sparsity in the ResNet 18 and wide ResNet. When measuring adversarial accuracy, two attack methods of PGD were used in our experiment. For each model, various defense methods such as augmentation, SPS, FS, and codmix were applied. Specifically looking at the wide ResNet 70, using codmix DDPM defense, the accuracy was better than all other cases. However, for sparsity, it had quite bad result. This shows that the adversarial accuracy metric is not very good at checking for the sparsity attack. One more thing is that SPS defense method was very robust against the sparsity metric. This shows that sparsity smoothing techniques of SPS was very robust against our L infinity attacks. Conclusion: in a recent study, adversarial accuracy was not sufficient to capture all robustness properties. So we proposed a new metric that captures various robustness properties for adversarial attack, sparsity. Thank you.